Right now, you are plunging through a gigantic hollow in space, almost 2 billion light-years wide. Astronomers confirmed its existence in 2013, yet most people have never even heard of it. We live inside what is called the KBC Void, a cosmic desert where matter is about 20% scarcer than it should be. That scarcity subtly distorts the way we measure reality. Inside this region, the universe seems to expand faster than it does elsewhere, creating contradictions in equations that were once considered rock solid. Our journey begins with the discovery that overturned long-standing assumptions, explores why most of the universe is essentially empty, and reveals what it means to occupy the remote outskirts of the cosmic landscape. The revelation started when three astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, set out to count galaxies. In 2013, after examining 35,000 galaxies spread across billions of light-years, they noticed something that shouldn't have been possible. Wherever they looked near our region of space, the expected number of galaxies simply wasn't there. Not a slight shortfall, but a full 20% fewer. The underdensity extended in all directions for nearly 1 billion light-years, forming an enormous bubble of space with us sitting not exactly at the center, but close enough to be deeply affected. This wasn't a small gap between clusters. It was a void of a size that standard cosmology claims should be extraordinarily improbable. Even detailed computer simulations rarely create voids this large unless they begin with extremely rare initial conditions. Some calculations suggested such a deficit would represent a 10 sigma deviation so unlikely that it might not occur even once in the entire observable universe. And yet, here we are, living inside one. The implications were immediate. If our cosmic address is so unusual, could it be biasing every measurement we make? When astronomers observe distant supernovae to determine how quickly the universe expands, are they measuring the true cosmic expansion rate, or only the distorted version inside our local environment? The existence of the void suddenly offered a possible solution to the infamous Hubble tension, the stubborn 9% difference between the expansion rate inferred from the early universe and the rate measured nearby. Both measurements are precise, both should agree, and yet they don't. But if we reside inside a huge underdense region, gravity from the denser material surrounding the void would tug outward on everything inside it. That extra pull would make galaxies within the void drift away faster than average, making the local expansion seem artificially high. In that case, we are not miscalculating the universe. We are simply measuring it from inside a gravitational anomaly. This raised an uncomfortable question. If our location is truly this peculiar, how much of our cosmological understanding can we trust? To answer that, scientists had to examine what voids actually are. Despite the name, they are not completely empty. Instead, they contain thin smatterings of hydrogen gas, faint traces of dark matter, and the ever-present influence of dark energy. Their density is so low that gravity barely has anything to work with. Without enough mass to draw matter together, new clusters stop forming, and existing structures hardly evolve. A void remains a void. Gravity, already the weakest known force, becomes even less relevant here, and dark energy dominates. In denser parts of the universe, gravity slows the expansion slightly. Inside voids, dark energy wins the tug-of-war completely, causing these regions to expand faster than average. They behave like cosmic bubbles, pushing their boundaries outward, while the surrounding filaments act like walls. Observations support this. Galaxies near the edges of voids move outward more quickly than the standard cosmic expansion can account for. Something is pushing them away from the center, and that something is the gravitational pull of the surrounding dense regions. If you imagine the void as a valley surrounded by mountains, gravity pulls downhill from the mountains toward the valley. But in the context of space, that pull makes galaxies drift outward rather than inward. The effect is measurable. The Milky Way itself is speeding away from the local void at around 600,000 miles per hour. Inside such a sparse environment, even the path of light behaves differently. Light traveling through a void experiences less gravitational redshift, making patches of the cosmic microwave background slightly cooler. These colder spots line up precisely with the locations of large voids we observe today. The match is not coincidental, it is a direct consequence of the physics of emptiness. Understanding voids reveals why they matter so profoundly. They are not just the dull spaces between interesting galaxies. They are natural laboratories where dark energy's influence becomes dominant and where gravity nearly fades from relevance. Comparing how matter behaves inside voids versus in dense regions offers powerful tests of fundamental physics. Our home inside the KBC Void may feel unsettling because it challenges the idea that we occupy an average place in the universe, but it also gives us a rare vantage point to study extreme low-density environments firsthand. The larger cosmic structure that contains these voids is far stranger than scientists once imagined. The universe isn't an even sprinkling of galaxies, it resembles Swiss cheese or a vast foam. Dense regions assemble into walls and filaments, while enormous hollow spaces take up most of the volume. This network of filaments, nodes, and cavities is known as the cosmic web, the largest structure in existence. Galaxy clusters gather at the intersections of filaments, and long chains of galaxies stretch between them for hundreds of millions of light-years. Voids lie between these structures, filling roughly 90% of the universe's volume while holding only a tiny fraction of its matter. It took decades for this intricate architecture to become clear. Early sky surveys lacked the depth to reveal the true three-dimensional layout. Galaxies that looked close together on the sky could be separated by billions of light-years. Only when astronomers began systematically measuring galaxy redshifts in the 1970s and 80s did the cosmic web snap into focus. Later surveys, especially the Sloan Digital Sky Survey, produced breathtaking 3D maps showing filaments twisting like cosmic tendons and voids appearing as vast black pockets. Structures like the Sloan Great Wall, a filament 1.5 billion light-years long and supervoids nearly 2 billion light-years wide, revealed a universe organized on scales no one had predicted. This web traces its origins back to the earliest fractions of a second after the Big Bang. Tiny quantum fluctuations caused some regions to start slightly denser and others slightly thinner. These differences were incredibly small, but gravity amplified them. Denser spots accumulated more matter, while sparse regions lost what little they had. Over hundreds of millions of years, those faint ripples grew into the filaments, clusters, and voids we see today. The result is a cosmos dominated not by matter, but by emptiness, punctuated by isolated concentrations of galaxies. The KBC Void is simply one bubble within this vast foam, but because we live inside it, it defines what we observe. The Milky Way isn't exactly at the center. Estimates place it 2 to 400 million light-years off-center, but compared to the void's billion light-year radius, that offset is relatively small. We are deeply embedded in this underdense environment, surrounded by low-density space in every direction. If we lived outside the void, in one of the dense filaments, our measurements of cosmic expansion would look completely different. The Hubble tension wouldn't exist. Even the structures around us participate in this unusual setting. The Milky Way is part of the local group, which sits within the Laniakea supercluster, a colossal structure containing around 100,000 galaxies spread across more than 500 million light-years. Yet even this enormous supercluster still resides inside the KBC Void. The void is so vast that it can swallow entire superclusters and barely notice. The local group is also influenced by a neighboring underdense region called the local void. Our galaxy is racing away from it at 600,000 miles per hour due to gravitational pulls from denser regions beyond, adding extra motion on top of the universe's expansion. These local motions complicate efforts to measure the true expansion rate, and inside an enormous void, these complexities only grow. Measurements of galaxy movements out to hundreds of millions of light-years show large-scale flows that are stronger than standard cosmology predicts. Entire regions of space drift in coherent patterns shaped by the gravitational imbalance created by the void. Nothing inside it sits still. Everything participates in the slow outward drift caused by the uneven distribution of matter surrounding us. Galaxies inside the void are not sitting idly. They are actively responding to the gravitational landscape around them, accelerating outward from the underdense center toward the denser structures beyond the void's edges. This makes our local patch of the universe far more dynamic and unusual than the smooth, uniform cosmos that standard models typically assume. Our location within the void also subtly shapes what we see. Light traveling from distant galaxies to our telescopes passes through this low-density region, encountering weaker gravitational influences than it would in a denser area. That reduced gravity slightly alters the light's wavelength and energy, producing subtle but measurable effects. The void also impacts the apparent distribution of matter. From our vantage point inside it, we see a surrounding shell of denser material in every direction, a ring of galaxy clusters and filaments at a characteristic distance. Beyond this shell, space gradually returns to the typical cosmic density. This creates an observational bias. We are not observing a random location in the universe, but rather one of its most extreme features. Living inside such a void introduces systematic uncertainty into every measurement we make. Even the most carefully measured expansion rates of the universe may be skewed not because astronomers are careless, but because our vantage point distorts the signals we receive. This discrepancy is most evident when comparing the two primary methods of calculating the Hubble constant, which measures the universe's expansion rate. One approach uses the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, to infer the early universe's density and expansion. Plugging this information into cosmological models predicts a present-day expansion rate of roughly 67 kilometers per second per megaparsec, meaning for every 3.3 million light-years of distance, space expands by 67 kilometers per second. The second method relies on nearby standard candles, such as type Ia supernovae and Cepheid variable stars, whose intrinsic brightness is known. By comparing their observed brightness with their expected brightness, astronomers calculate their distances. Combining those distances with measured redshifts yields the local expansion rate, consistently higher at about 73 kilometers per second per megaparsec. The difference, 9%, may seem small, but is statistically significant, with a 5 sigma confidence level, meaning there is less than a 1 in a million chance that it arises by chance. The KBC Void offers a natural explanation. Local measurements fall within the underdense region, where gravity from surrounding denser matter pulls galaxies outward, boosting their apparent recession velocities. Galaxies appear to move faster than they would in a typical region, inflating the locally measured Hubble constant. Essentially, we are measuring the expansion of space plus the peculiar motion induced by the void's gravitational imbalance. Models of a void matching the KBC's size and depth show that this effect is large enough to reconcile the local and global measurements. Yet this explanation challenges long-held assumptions. The cosmological principle, the idea that the universe looks roughly the same from any location, suggests we occupy no special position. Finding ourselves inside a supervoid that measurably alters cosmic observations seems to contradict that principle. Humanity has gradually been removed from any central cosmic role. Earth is not the center of the solar system is not the center of the galaxy, and the galaxy is not the center of anything. Now, we must confront the possibility that our local environment is unusually empty on a cosmic scale, a conclusion that makes many researchers uneasy. Despite the discomfort, the evidence is compelling. The void exists, measurements disagree, and the void's influence aligns precisely with observations. The apparent Hubble tension is therefore not simply a measurement error, but a reflection of our cosmic context. Its implications run deep. The universe's expansion rate sets the timeline for everything else in cosmic history. If the local expansion is higher than previously assumed, the universe might be younger than 13.8 billion years, potentially only 12.7 billion. This conflicts with observations of ancient stars in globular clusters, some of which appear older than the implied age, creating a fundamental puzzle. It also affects our understanding of dark energy, which dominates roughly 68% of the universe. Variations in expansion rates could imply that dark energy behaves differently than standard models suggest, potentially evolving over time rather than remaining constant, a revolutionary possibility. Other explanations for the tension have been proposed. Perhaps systematic errors persist in distance measurements, such as dimming of supernovae by intergalactic dust, or environmental effects on Cepheid variables. Or maybe general relativity behaves slightly differently on cosmological scales, requiring modifications to gravity itself. However, each of these alternatives introduces complex assumptions, whereas the void hypothesis offers a simpler, observationally grounded solution. Our unusual location skews the local measurements without changing fundamental physics. Recent studies strengthen this case, showing that the outflow velocities from the void also match observed motions of nearby galaxy clusters. The hypothesis makes testable predictions, many of which are being confirmed. The physics of voids is counterintuitive but explainable. Gravity does not reverse, it always attracts. But inside a void, galaxies are pulled outward because nearly all the matter lies outside the underdense region. Imagine standing in a shallow valley, surrounded by mountains. The gravitational pull is toward the mountains, away from the valley floor. Similarly, galaxies inside a cosmic void accelerate outward toward denser filaments and clusters. This creates a systematic velocity field that can be measured. Redshift and distance estimates show that galaxies near the void center move faster than cosmic expansion alone would predict, with the effect decreasing toward the edges. In the KBC Void, this outflow contributes hundreds of kilometers per second to galaxy velocities. Our own Milky Way participates in this cosmic flow. It is moving roughly 600,000 miles per hour away from the nearby local void, influenced by the imbalance in surrounding gravity and supplemented by pulls from structures like the Virgo cluster. Even at such staggering speeds, covering over 5 billion miles each year relative to the void is so immense that our motion barely makes a dent. Crossing it would take hundreds of millions of years, and meanwhile, the void continues to expand due to dark energy faster than we could ever escape. For the foreseeable cosmic future, we remain embedded in this underdense region, moving through a dynamic landscape shaped by the subtle but powerful pull of distant matter. The Milky Way's motion through space is influenced by multiple gravitational factors, and one of the largest contributors is the local sheet. This flattened structure of galaxies, which includes the Milky Way, Andromeda, and nearby neighbors, forms one boundary of the local void. The entire sheet is flowing outward from the void center at roughly 260 kilometers per second, about 580,000 miles per hour, and our galaxy participates fully in this bulk motion. The sheet is not static, it is gradually evacuating from the void, flowing outward like water draining from a depression. This process has been ongoing for billions of years, and will continue for billions more. Yet escaping the void is only part of the Milky Way's motion. The galaxy is also being drawn toward the Virgo cluster, a massive concentration of over 2,000 galaxies, located about 60 million light-years away. Its gravitational pull adds roughly 250 kilometers per second toward Virgo. On top of that, the Milky Way and Andromeda are moving toward each other and will collide in approximately 4 billion years, adding yet another component to our velocity. When all these influences are combined, the Milky Way's total peculiar velocity relative to the cosmic microwave background, CMB, rest frame comes to about 627 kilometers per second. This is the speed astronomers detect when observing the dipole pattern in the CMB temperature. These motions are not just curiosities, they complicate cosmological measurements. When astronomers observe distant galaxies and measure their redshifts, they must correct for our own motion through space. Otherwise, galaxies in the direction we are moving appear slightly blue-shifted, while those in the opposite direction appear red-shifted, creating a misleading pattern that could mimic large-scale cosmic structure. Such corrections have been routine for decades, but inside a void, they become far more complex. The void itself generates enormous bulk flows extending hundreds of millions of light-years, and separating this effect from true cosmic expansion requires precise modeling of the local velocity field. Our high speed through space also serves as compelling evidence for the void. If we were in a typical region of average density, the Milky Way's peculiar velocity would be much smaller, perhaps only 100–200 kilometers per second. The fact that we are moving so fast indicates strong gravitational gradients in our neighborhood, precisely what would be expected if we were near a massive underdense region. This motion is consistent with the KBC Void hypothesis and would be difficult to explain otherwise, making our velocity a key piece of evidence in understanding the void's existence and influence. This principle asserts that the universe is homogeneous and isotropic on large scales, meaning it is roughly the same everywhere and in every direction, with no location or direction being special. If you want to explore more mysteries like this and see the cosmos in a whole new way, make sure to like and subscribe. The universe is waiting, and we're just getting started.